Billions of years ago, our planet may have frozen from pole to pole, a true Snowball Earth. Oceans turned to ice, sunlight dimmed, and life itself nearly vanished. But how did it happen? Today we'll uncover the science behind Earth's greatest deep freeze. If you enjoy this story, please like, subscribe, and share, and tell us in the comments, could life really survive a frozen world? Thank you for watching. Now let's begin. The frame begins at the scale of star and orbit, where the amount and pattern of sunlight that reach Earth set the outer limits within which any climate can unfold. During the Neo-Proterozoic, the sun is a little dimmer than today because stars like the sun brighten very slowly as they fuse hydrogen over deep time. The decrease is only a few percent, yet on a whole planet the change is meaningful, since it alters how close the climate sits to thresholds that separate mild states from icy ones. The average distance between Earth and the Sun stays essentially the same, so the spread of sunlight with distance does not change in a way that would move the planet out of its familiar orbital zone. What does change on the timescales of tens to hundreds of thousands of years are the parameters that shape the seasonal and latitudinal pattern of incoming energy. Insolation is the word for the flow of solar energy reaching the top of the atmosphere. Even with a slightly dimmer sun, the geometry of a nearly spherical planet still gives the equator the highest average insolation and the poles the lowest, because sunlight meets low latitudes more directly and high latitudes at a slant. The way that geometry combines with the rhythm of the seasons depends on three orbital properties. Eccentricity is the shape of Earth's path around the Sun from almost circular to slightly oval. When eccentricity is higher, the difference between sunlight at the closest approach and at the farthest point grows, and the season that occurs near the closest approach becomes a little stronger in that hemisphere. Obliquity is the tilt of Earth's spin axis relative to the plane of its orbit. Greater tilt strengthens summers and winters at high latitudes, while smaller tilt weakens them. Precession is the slow wobble of the spin axis that changes which hemisphere points toward the Sun at the closest approach. Together, these cycles shift when and where sunlight is strongest, without changing the long-term annual global average by more than a very small amount. In the Neo-Proterozoic, these cycles operate within ranges similar to today, so the planet experiences familiar patterns of strong summers, dark winters, and a marked contrast between low and high latitudes. The slight dimming of the sun serves as a baseline reduction, upon which the orbital cycles lay alternating intervals of stronger and weaker seasonal contrast in each hemisphere. Day length is another outer parameter that matters because it shapes atmospheric motion. Tidal friction with the moon gradually lengthens the day over geologic time, so in the Neo-Proterozoic, the day is somewhat shorter than the modern day. A shorter day means a faster rotation rate and a slightly stronger Coriolis effect, the apparent deflection that acts on moving air and water. That effect helps set the width and placement of the tropical rising branch and the subtropical belts where air descends. While the detailed winds and currents belong to the next layers of the climate system, the faster spin at this time is part of the outer frame that any circulation must follow. The tilt also sets the locations of the Arctic and Antarctic circles, the latitudes beyond which there is continuous daylight in summer and continuous darkness in winter. Small changes in tilt move these circles slightly and change the area subject to extreme light and dark seasons. The placement of those circles matters because polar darkness allows winter cold to build rapidly, while continuous summer light offers a chance to reverse it. At the same time, Earth's near-spherical shape locks in a rule that no orbital configuration can break high latitudes, receive much less annual insolation than the tropics. Over tens of thousands of years, precession moves the timing of closest approach through the seasons. When closest approach aligns with a hemisphere's summer, that hemisphere receives somewhat stronger summers and somewhat colder winters. When it aligns with winter, summers are weaker and winters milder. Over many cycles, alignments can cluster to give intervals where summers in one hemisphere are persistently less able to remove snow left by winter. Under a sun that is a little dimmer, the margin for summer melt is smaller, so these alignments become more influential. Eccentricity modulates how much difference precession can make. When the orbit is close to circular, the timing of closest approach matters little. When the orbit is more oval, precession matters more. Meanwhile, obliquity controls the basic contrast of the high latitude seasons. Lower tilt cools high latitude summers, warms winters slightly, and makes it easier for seasonal snow to persist from one year to the next. Higher tilt does the opposite by boosting summer sunlight where it is most needed to remove snow. These changes do not dictate any specific climate outcome on their own. They define a shifting pattern of where and when Earth receives energy from the sun, and they determine how close summers at high latitudes come to the threshold required to melt seasonal snow and sea ice. The spectrum of solar radiation arriving at the top of the atmosphere is nearly the same as today, so the interaction of light with air ice, water and land follows familiar physical rules. Bright snow and clean ice reflect much of the visible part of sunlight. Open ocean absorbs most of what reaches it, and bare rock sits between those extremes. Clouds and aerosols influence how much sunlight reaches the surface, but even those interior agents respond to the outer pattern of warming set by insolation. The upper boundary then can be stated plainly. The sun delivers slightly less power than today. Earth turns a little faster and orbits the sun in a path that shifts its orientation and shape on timescales, long compared to a single season but short compared to the age of continents. The tilt sits within a familiar range strong enough to produce polar day and polar night, yet not so large as to invert the seasonal structure of the tropics. The geometry alone sets a latitudinal gradient of incoming energy, with abundant light in the tropics and meagre light near the poles, and the orbital cycles shift the strength and timing of seasons so that some intervals favour colder high-latitude summers. Within this outer framework, the climate system must work with what it receives. Where sunlight is scarce long, winters bring deep darkness, and weak summers must work harder to remove the ice and snow they inherit. Where sunlight is abundant day after day of high-angle light, pours energy into the surface and builds heat that winds and currents can carry away. Across the globe, the slightly dimmer sun reduces the headroom above the thresholds that separate states with limited seasonal ice from states with more persistent ice. The planet's boundary conditions do not prescribe an icy world by themselves, but they set the stage by shaping the energy that arrives, the seasons that divide it, and the rotation that guides the air and the sea as they carry it away. The long view of climate rests on a slow exchange of carbon among the atmosphere, the ocean, the crust and the mantle, and this exchange sets the background within which any shorter shift must operate. On land, the central process is silicate, weathering the family of reactions by which minerals that contain silicon, calcium, magnesium, sodium and potassium break down in the presence of water and carbon dioxide to form clays and dissolved ions. When carbon dioxide dissolves in rainwater, it forms carbonic acid, which seeps into soils and along fractures, attacks mineral bonds and frees calcium and magnesium that later combine with bicarbonate to make carbonate ions carried by rivers to the sea. This pathway removes carbon from air and transfers it to dissolved pools and ultimately to carbonate rock. So geologists call it the carbonate-silicate cycle and describe it as a thermostat, because the rate of removal depends on temperature and runoff in warm, wet conditions, chemical reactions proceed faster. Soils carry more dissolved carbon to streams, and rivers deliver a larger carbonate load to the ocean. In cool, dry conditions, reactions slow, soils thin, and the delivery weakens. The state of life on land influences this chemistry by setting how much carbon dioxide builds up in soils and how much water and acid touch fresh mineral surfaces. In the Neoproterozoic, there are no forests, so the strong biochemical acceleration of weathering seen under deep modern soils is absent. Yet microbial mats, lichens, and thin crusts can still promote mineral alteration at the grain scale, while frost cracking, thermal stress, and physical erosion expose new surfaces that sustain reactions. Grain size matters because fine particles provide large areas over which fluids can react, and uplift matters because it brings unweathered rock to the surface. Where erosion is rapid, unaltered material constantly appears, and where relief is low, weathering may rely on slow penetration of fluids into old regolith, so the pace of supply and the pace of reaction co-limit removal. Rivers link land to ocean and deliver dissolved calcium, magnesium, and bicarbonate that raise seawater alkalinity, which is the capacity of water to neutralize acids and to support carbonate ions. When alkalinity and carbonate concentration exceed the level at which minerals are stable, carbonate muds form abiotically or within microenvironments built by microbial communities that shift local chemistry, and with burial these muds lock carbon into rock for spans that reach from hundreds of thousands to many millions of years. Organic carbon burial adds a second, slower removal path. Photosynthetic organisms fix carbon dioxide into biomass, most of which returns to inorganic form through respiration and oxidation, yet a small fraction escapes destruction and is buried in sediments. Over very long times, that burial is linked stoichiometrically to the buildup of oxygen in air, though the exact balance in the Neoproterozoic varies with ecology and redox conditions in basins and shelves. A complementary sink works within the sea floor, where seawater circulates through hot young basalt near mid-ocean ridges. As fluids percolate, they react with the crust, consume carbon dioxide, and precipitate carbonate minerals in veins and pores. So seafloor weathering stores carbon directly within oceanic plates. The rate depends on the temperature of circulating fluids, the permeability of rocks, and the vigor of hydrothermal convection that is driven by heat from underlying magma. And because hotter fluids and faster flow increase reaction rates, warmer oceans and more active circulation strengthen this sink, while colder oceans and sluggish flow weaken it. Against these removals stand the long steady sources from deep earth volcanic degassing. At arcs and hotspots releases gases derived from the mantle and from recycled sediments, while metamorphic devolatilization in thickened crust and in subduction zones breaks down carbonate and organic bearing rocks and liberates carbon dioxide that reaches the surface through vents and diffuse emissions. These inputs drift over tens of millions of years with the tempo of crust production and mountain building, but on the time window of a single climate episode they appear nearly constant compared to the more climate-sensitive weathering terms. Because the climate-driven sinks speed up in warm wet states and slow down in cold dry states, departures from balance are resisted. If surface temperature rises, reaction rates increase. Runoff increases and removal of carbon dioxide accelerates until the greenhouse effect eases back. If surface temperature falls, reactions slow, soils thin, and removal slackens, while deep sources continue, so atmospheric carbon dioxide gradually accumulates and strengthens the greenhouse effect until the energy balance returns toward the previous range. This restoring behavior operates over long intervals because rocks react and sediments accumulate slowly, so the time to approach a new steady state spans hundreds of thousands to millions of years, and the atmosphere and upper ocean act as the fast leg that adjusts quickly to changes in flux, while crust and mantle act as the slow leg that integrates those fluxes over geologic time. Under a sun that is slightly dimmer than today, the background greenhouse needed to maintain liquid water at the surface is higher than it would be under modern brightness, and the carbonate-silicate cycle supplies that greenhouse by allowing atmospheric carbon dioxide to rise to the level required to balance outgoing radiation when weathering is inefficient, and by drawing it down when weathering is efficient. Water vapour contributes to warming as well, but because its concentration depends strongly on temperature, it acts as a fast amplifier rather than a control knob, while methane is produced where oxygen is scarce, and organic matter decomposes in the absence of oxygen, and is destroyed photochemically in an oxygenated sky. So in the late Neoproterozoic, it likely plays a secondary, shorter-lived role compared to carbon dioxide. The reservoirs that store carbon differ in size by many orders of magnitude, with the mantle holding the largest inventory, crustal carbonates holding an immense mass, the ocean holding a large dissolved pool, and the atmosphere holding the smallest active share. The fluxes that connect these reservoirs are small relative to the stocks, so even modest changes in removal rate can shift atmospheric carbon dioxide over long windows, without requiring dramatic changes in the deep sources. Seen in this way, the long-term carbon cycle defines a moving target rather than a single fixed point. The target is the atmospheric carbon dioxide level, at which weathering and burial balance metamorphic and volcanic supply under the prevailing temperature, rainfall-exposed rock types and biological activity, and when any of those boundary factors shift, the target shifts as well, and the system moves toward it on slow schedules set by reaction kinetics and sedimentation. In the Neoproterozoic, that target is set by the same chemistry that operates today, by the same coupling of heat water and mineral reaction, and by the same logic that makes carbon dioxide both a greenhouse gas and a reactant that is consumed when silicate minerals break down. Within those rules, the deep cycle supplies a baseline greenhouse that supports clement conditions when removal is weak and relaxes when removal is strong, and it provides the stable backdrop of fluxes and reservoirs against which other parts of the climate system must work. Geography sets the canvas upon which light air and water must move, and in the Neoproterozoic the arrangement of continents and oceans differs strongly from the modern pattern in ways that matter for reflectivity, wind systems, currents, and the exchange of heat between low and high latitudes. The supercontinent known as Rodinia, assembled earlier in Proterozoic time, stands in the late stages of its life and begins to fragment into large cratonic blocks, separated by new rift basins and young oceanic crust. As rifts open, long continental margins with broad shelves develop while interior regions remain high and rugged along old mountain belts. Many reconstructions place substantial areas of land at low latitudes with continental cores and wide coastal plains crossing the tropics where sunlight is most intense. The presence of large land masses in the tropics alters albedo because bare rock soil and seasonal snow on land reflect light differently from open ocean. If snow or thin ice reaches low latitudes during cold seasons, bright surfaces form where incoming light is strong, so the fraction of sunlight bounced back to space rises sharply, compared to a world with dark tropical water. The pattern of land also shapes rain belts and deserts by guiding the moist air that rises near the equator and the dry air that sinks on either side of the tropics. Where continents sit beneath the rising branch, tropical rain falls inland and sustains rivers that deliver fresh water and sediment to shallow seas. Where continents sit beneath descending air, arid belts form with strong dust sources that feed the atmosphere and brighten the top of clouds. The distribution of mountains and plateaus matters because high terrain cools with altitude, accumulates seasonal snow and reroutes winds. Ranges aligned across the path of prevailing flow force air to rise lose moisture and descend drier on the lee side, carving rain shadows that can extend far across continental interiors. Along new rift margins, the coastline length increases and the continental shelf widens, creating large areas of shallow water where seasonal ice can form and break up repeatedly, and where tidal and wind mixing can expose the ocean surface to cold winter air. Shelf geometry affects heat uptake because shallow water stratifies and mixes differently from deep ocean, and when cold air masses sweep across wide shelves, the exchange of sensible and latent heat can be efficient, cooling surface water and favouring seasonal ice that raises albedo near coasts. Ocean gateways between the rifted blocks govern the pathways available to currents that move warm water toward higher latitudes and return colder water equatorward at depth. When gateways are narrow or blocked by continental promontories, the continuous bands of zonal flow that circle a latitude can be interrupted, and meridional exchange can be limited to particular choke points where tides and eddies do the work of mixing. If a configuration allows a broad equatorial seaway strong east to west, currents can develop that concentrate warm surface water and pile it against western margins, while eastern margins experience upwelling of colder water. If continents interrupt the equatorial band, warm water transport across basins weakens, and eastern upwelling zones can expand, drawing cold nutrient-rich water toward the surface over larger areas. At higher latitudes, the presence or absence of circumpolar passages influences how efficiently the ocean can isolate polar surface water from low-latitude heat. If a ring of water can flow uninterrupted around a pole, currents can develop that reduce north-south heat exchange and allow polar surface layers to remain cold and fresh. If continents block such rings, boundary currents that slide along continental slopes carry tropical warmth poleward more readily. The balance of these pathways in the Neoproterozoic depends on the evolving positions of cratons and the opening widths of new oceans, so the same forces that break a supercontinent also rearrange the corridors through which the ocean breathes heat. Bathymetry interacts with wind and buoyancy at the surface to set where deep water forms and where it returns to depth after cooling. When cold, salty water becomes dense enough to sink on broad shelves, it can drive overturning that ventilates the deep ocean and delivers cold to depth, while if shelf areas are restricted and fresh water input is high, surface layers can remain stratified and insulated from exchange. The low-latitude placement of land matters here as well, because tropical weather patterns control how much rain and river discharge enter particular basins, and that fresh water input can cap the ocean with a lens that resists mixing even under cold air. Sea level stands also affect shelf area, yet on the time window relevant to a single long glaciation. The major agent is the shape of continents themselves, rather than slow changes in the global waterline. The arrangement of land and sea further governs the tracks of storms that carry heat poleward in the atmosphere. Wide oceans flanked by low-latitude continents foster strong monsoon systems, where seasonal heating contrasts draw air inland in warm months and back to sea in cool months. This alternation influences how and when clouds form over land versus water, which in turn modulates reflectivity, because bright cloud tops send sunlight back to space, while gaps allow dark surfaces to absorb it. Where continents straddle subtropics, arid belts can widen, and surfaces with sparse vegetation exhibit higher reflectivity and stronger daily temperature swings that feed dry convection. Dust lifted from dry basins interacts with radiation and clouds, yet the sign and size of that interaction depend on altitude and particle properties. The geometric point remains that continental placement sets the dust source map and the common paths that rising and sinking air must follow. In the Neoproterozoic old mountain belts produced by earlier collisions retain high ground that stands above adjacent basins, and weather cut through these belts feeds sediments to the new margins, where wide shelves accumulate long wedges of sand and mud. The texture of these deposits influences coastal shape and nearshore currents, while isostatic responses to erosion and sediment loading warp local sea level and the depth of shelves, all within the broader control of plate motion. Taken together, the paleogeography of a fragmenting Rodinia produces a world with extensive tropical land, long shelf-lined margins, evolving ocean gateways and persistent highlands. This geometry enhances the potential for bright surfaces to occupy low latitudes. When seasonal ice and snow advance concentrate strong land, see thermal contrasts in the belt of maximum sunlight, and channels both wind and water along new paths that differ from modern routes. The atmosphere and ocean that move across this surface must conform to these boundaries, spreading heat where corridors allow pooling cold, where barriers resist, and building clouds where uplift and humidity meet. Because incoming sunlight is strongest near the equator, any brightening of tropical surfaces has an outsized effect on the fraction of energy absorbed by the planet, while any expansion of upwelling or shallow mixed layers in those same latitudes alters how efficiently the ocean can store and release heat through seasons. The supercontinent geometry thus fixes the spatial frame for albedo, the texture of coastlines, and the placement of storm tracks and currents, and it does so with a pattern that loads a large share of area into the latitudes where the balance between reflection and absorption matters most for the planetary energy budget. At the heart of a planet prone to freezing lies a simple property of surfaces under sunlight. Bright surfaces reflect more energy than they absorb, while dark surfaces do the opposite. The fraction reflected is called albedo. Snow and clean ice have high albedo, so they bounce much of the visible part of sunlight back to space. Open ocean has low albedo, especially when the sun stands high, so it takes in energy and warms. Bare rock sits between these extremes and shifts with moisture, grain size, and angle of light. The ice albedo feedback is the loop formed when cooling allows snow and ice to expand. Expansion raises albedo raised. Albedo reduces absorbed energy, and reduced energy leads to further cooling and further expansion. Warming reverses the steps retreat of snow, and ice lowers albedo lower. Albedo increases absorbed energy, and the added energy supports more retreat. A feedback becomes powerful when small nudges in temperature move the boundary between bright and dark over large sunny areas. In a world with much land near the equator, seasonal snow can reach low latitudes during cold intervals, and thin sea ice can spread across shelves and into tropical waters under long nights. Because sunlight is strongest in the tropics, even a modest brightening there carries an outsized penalty for global absorption compared to changes confined to high latitudes. The physics that govern thresholds are plain. The surface energy balance at any location is the difference between incoming sunlight that survives atmospheric scattering and reflection, minus the reflected share at the surface, plus the net exchange of infrared radiation between surface and sky, plus exchanges of heat with the air and of latent heat with evaporation or condensation, plus any conductive flux within the uppermost layer. Snow and ice alter several of these terms at once. By reflecting sunlight, they cut daytime gains. By presenting a cold surface, they reduce upward infrared radiation until the surface warms or the sky clears. By capping the ocean, they limit evaporation and the moisture that would otherwise feed clouds and snowfall elsewhere. Sea ice also insulates the ocean from frigid air, slowing the winter loss of ocean heat once a thick cover is in place, yet the same cover must first be built by the very losses it later resists. When sea ice is thin, heat conducts upward easily and winter growth accelerates. When sea ice thickens by a meter or more, conduction slows, growth tapers, and additional thickening demands many cold days. Snow that settles on top further raises albedo and reduces growth by insulating the ice. On land, the persistence of snow depends on whether summer days deliver enough energy to remove what winter leaves behind. The threshold is crossed when the snow line, which is the altitude above which snow survives through summer, descends to low elevations and reaches broad uplands or coastal plains. Once summer fails to clear these surfaces, the following autumn begins with a bright base that cools. The local air mass lengthens the cold season and makes it easier for early snows to survive. Glaciers form when snow that persists compacts into firn and then into ice, and the growth of glaciers raises local albedo further, while increasing the height of their surfaces, which cool with altitude and strengthen persistence. The feedback is not uniform because clouds can both brighten and dim the planet depending on type, altitude, and season. Low, thick clouds reflect a great deal of sunlight and tend to cool the surface beneath during the day, while high, thin clouds allow more sunlight through and contribute to greenhouse trapping of infrared energy. Over bright snow, additional cloud reflection may offset only a small further share, because much light is already bounced away, while the infrared effect can matter during long polar nights. Over dark ocean, the same low clouds can make a large difference to daytime absorption. Thus, the net cloud response to expanding ice can either amplify or soften the feedback depending on the prevailing cloud field moisture supply and circulation. But it does not erase the geometric fact that replacing dark tropic waters or soils with bright snow or ice lowers energy intake. The presence of dust and volcanic ash can darken snow grains and reduce albedo locally, yet as a planet cools, and moisture transport weakens, the delivery of impurities to remote ice can decline, so dusting does not guarantee a stable low reflectivity blanket. The ice albedo feedback also carries memory, a property called hysteresis. There can be more than one stable climate state under the same amount of sunlight and greenhouse strength, because the reflectivity map depends on where ice already sits. If the planet starts warm and snow lines are high, summers remove most seasonal snow and sea ice retreats far from low latitudes, so the annual mean albedo remains low, and the same greenhouse level supports liquid oceans and limited permanent ice. If the planet starts cold with expanded ice, summers may not reach the energy needed to clear the bright surface, so the annual mean albedo remains high, and the same greenhouse level may fail to restore warmth. To move from the cold state back to the warm state, the system may require a larger increase in absorbed energy than the decrease that first tipped it into cold. This gap between the forward and backward thresholds is the signature of hysteresis. The gap widens when bright surfaces occupy low latitudes, narrows when bright surfaces are confined to high latitudes, and shifts with slow controls such as solar brightness and the rotation rate that shapes winds and currents. Sea ice introduces an additional threshold through its interaction with ocean heat content. The ocean stores a large reservoir of heat in its upper layers. If winters repeatedly draw more heat out of the mixed layer than summers can return, the mixed layer cools year by year, and sea ice forms earlier and melts later until a perennial cover develops. Once perennial ice is present across wide belts, summer sunlight must first melt the surface and thin the cover before any significant ocean warming can begin, a task made harder when the snowpack absorbs little energy. In contrast, if perennial ice retreats and summers allow open water to develop wind and waves, mix heat into the upper ocean, and store it against the next winter, delaying freeze and shortening the season during which the atmosphere can extract heat. The transition between these regimes revolves around the critical fraction of open water at summer peak and the timing of freeze onset, which together decide whether the ocean leaves summer with a surplus or a deficit. Land ice introduces longer thermal inertia, because thick ice sheets respond over centuries to millennia and reshape the land surface as they grow, carving basins and steepening slopes that alter wind and snowfall patterns. As they advance toward lower latitudes, they push the bright line farther into regions of strong insulation and strengthen the planetary feedback, even as local topography forces more moisture to rise and snow out along their margins. In sum, the ice albedo feedback is a structural feature of any planet with bright condensates and dark liquids under a luminous star. It defines thresholds by linking energy intake to the moving boundary between bright and dark. It carries memory through hysteresis that depends on prior ice extent. It interacts with clouds and impurities without losing its geometric leverage, and it operates through both fast sea ice responses and slower glacier and ice sheet changes. In the setting of the Neoproterozoic, with substantial land near the equator, wide shelves and a slightly dimmer sun, the same physics apply, and the position of the thresholds depends on how easily seasonal snow and sea ice can claim low-latitude surfaces and keep them bright through summer. Several processes can push a climate that already lies near icy thresholds into a deeper cool state, and in the Neoproterozoic, researchers examine a suite of candidates that act through known physical and chemical pathways. One proposed class of triggers operates by drawing down atmospheric carbon dioxide over spans long enough for the surface and ocean to adjust. When continents rift and later collide, mountain belts rise and erosion accelerates, exposing fresh silicate minerals that react rapidly with acidic water. If large tracts of newly uplifted rock sit in rainy belts, the delivery of calcium and magnesium to rivers increases, and the riverine flux of bicarbonate to the sea strengthens, so more carbon becomes locked in carbonate minerals. The effect strengthens when uplift and erosion refresh weathering zones faster than soils can armor them, keeping reactive surfaces in contact with water. The same logic extends to volcanic terrains formed by large igneous provinces. Basalt weathers faster than most granites because it holds more readily leached cations and presents abundant glassy and fine-grained faces. If vast basaltic plateaus erupt in or drift into the humid tropics, their accelerated dissolution can draw down carbon dioxide for hundreds of thousands to a few million years. Some reconstructions place extensive mafic provinces in low latitudes during the Cryogenian, a geometry that would amplify this sink by placing highly reactive rock beneath heavy tropical rains and warm temperatures that speed reaction kinetics. A complementary tectonic driver acts from the source side. The long-term supply of carbon dioxide from the mantle and from metamorphic breakdown varies with the rate at which new crust forms and with the thermal and chemical state of subduction zones. If ridge systems slow, or if the proportion of carbon-rich sediments carried to depth that liberate gas decreases the steady input to air, and sea can fall enough to shift the balance toward removal, even if weathering rates do not change. Over many millions of years, such supply changes are not constant, and if a minimum in degassing coincides with a maximum in weathering efficiency, the combined effect can lower greenhouse strength toward a tipping region. A third pathway involves nutrients that set the pace of photosynthesis and burial of organic carbon. If rifting uplift or weathering pulses increase the delivery of phosphorus and iron to shallow seas, primary production can rise, and with it the export of organic matter to the ocean floor. Where bottom waters are low in oxygen, more of that organic matter escapes oxidation and is buried. Each unit buried removes a stoichiometric share of carbon from the short-term cycle and allows a corresponding rise in oxygen, which in turn reduces the atmospheric lifetime of methane, because methane is destroyed more quickly in an oxygenated sky. Since methane is a strong greenhouse gas per molecule over short intervals, its decline reduces near-term warming and leaves carbon dioxide as the dominant long-lived control. The link from nutrient delivery to burial to methane loss provides a lever that can cool climate even if carbon dioxide changes only modestly. The ocean circulation itself can serve as a trigger when gateway changes or salinity and temperature patterns alter, where water sinks and how efficiently heat moves from equator to poles. If reorganized winds and currents reduce the poleward flow of warm surface waters, high latitudes cool and seasonal ice gains a head start. If the deep ocean becomes more isolated from the atmosphere, the return of stored heat to the surface slows, and winters can draw down the mixed layer temperature year upon year until summer energy no longer clears sea ice. Such circulation shifts need not be abrupt. What matters is their sign and persistence in a world already close to the snowline threshold. On timescales of years to decades, aerosols from explosive volcanism brighten the planet by increasing the reflection of sunlight in the upper atmosphere and by seeding low clouds. These effects cool the surface for only a few years per large eruption, yet a sustained interval with frequent high sulfur events, especially if aligned with orbital configurations that deliver weaker high-latitude summers, can allow snowfields and thin sea ice to expand enough that the ice albedo feedback takes a larger role during the following seasons. Over longer spans, the balance between volcanic aerosols that cool and volcanic carbon dioxide that warms depends on eruption style and cadence. The aerosol pulse fades quickly, while the added greenhouse gas accumulates until weathering draws it down, so short-lived cooling can only push the system if the background greenhouse has already declined. Orbital pacing provides another route by which relatively small external nudges can steer the climate toward ice expansion. When obliquity spends extended intervals at the low end of its range, summers at high latitudes become weaker, and more snow survives the melt season. If precession and eccentricity align so that summers in one hemisphere occur near the farthest distance from the sun, while winters occur near the closest point, seasonal contrast weakens, and the probability that snow persists increases. Over many cycles, such alignments can cluster and build cumulative snowpack on plateaus and wide coastal plains. Because the sun in the cryogenian is modestly dimmer than today, the amount of additional summer energy needed to clear snow is smaller than modern values, so the same orbital alignments carry greater leverage. Changes in dust supply can also favour cooling under certain arrangements of land and wind. If arid belts expand and dust sources intensify, reflected sunlight by dust layers can reduce surface heating in the tropics. In some settings, dust deposited on snow darkens it and encourages melt. But if circulation carries dust beneath bright cloud decks rather than onto snowfields, the net effect can remain cooling. The balance among these optical outcomes depends on particle size, altitude, and cloud fields set by geography. The point for triggers is that continental positions dominated by low-latitude land can load the atmosphere with particles that scatter incoming light at latitudes where the energy penalty is largest. The rise of oxygen during the Neoproterozoic may interact with these triggers by altering greenhouse chemistry. As oxygen consolidates in the atmosphere and ocean surface methane production in shallow sunlit waters faces stronger oxidation, and methane lifetime shortens, weakening a gas that otherwise would supplement carbon dioxide warming. At the same time, oxidation of reduced volcanic gases consumes oxygen and yields sulfate that can feed marine sulfate aerosols through biological and photochemical pathways. Those aerosols in turn can seed clouds and raise reflectivity. These are not independent levers, but linked parts of the same carbon, sulfur and oxygen cycles that respond to tectonic and biological pacing. Impact events and solar variability are sometimes discussed as additional initiators. Large impacts can throw reflective dust and sulfate into the stratosphere for years, and a sustained minimum in solar activity could marginally reduce the energy that reaches the top of the atmosphere. The geological record of the cryogenian does not require an impact or an unusual solar minimum to account for the long duration of cooling that follows, and any such short forcing would still need to hand off to slower feedbacks to maintain expanded ice. The parsimonious view treats impacts and intrinsic solar fluctuations as possible short-lived contributors that matter only if the climate is already perched near a threshold set by continents weathering greenhouse strength and circulation, in some plausible triggers for initial cooling cluster around processes that reduce greenhouse forcing through carbon dioxide drawdown and methane loss that limit poleward heat transport by changing winds and currents, or that raise planetary reflectivity through aerosols and clouds, all operating within boundary conditions already close to permitting seasonal snow and sea ice to invade low latitudes. Each mechanism has an established physical or chemical basis. Each can act alone or in concert, and none requires special physics beyond what is already present in Earth's coupled system. What decides their success is their timing magnitude and duration relative to the slow carbon cycle and to the feedbacks that link surface brightness to energy intake at the scale of a whole planet. An ocean capped by ice behaves as a layered and breathing system whose exchanges of heat, salt and gases are throttled by the thickness and texture of the cover. Sea ice begins as fragile tiny plates that form in supercooled wind-stirred water and gather into a slushy skin called grease ice. As sheets consolidate and thicken by congelation at the base, crystals trap pockets of brine that later connect into channels and veins that cut through the ice matrix. The salt locked in those pockets does not vanish. It migrates and drains, so the bulk salinity of the ice decreases as it ages, and the brine sinks into the ocean below. The rejection of salt during growth increases the salinity and density of the uppermost ocean, so winter formation of sea ice promotes sinking plumes and convection that carry cold into deeper layers. The converse occurs during summer melt when fresh water released from the surface layers of ice forms a lighter lens that stabilizes the water column and inhibits upward heat transport. This seasonal alternation builds a halocline, a salinity stratification that can persist beneath a perennial cover and decouple the surface from the heat stored below. The ability of ice to grow is set by the balance between conductive heat flow through the cover and the loss of heat to the atmosphere. When the cover is thin, conduction is efficient and growth is rapid. As the cover thickens, the gradient weakens and further thickening slows. Snow piled on top insulates the ice and reduces growth, while at the same time increasing albedo and cutting the share of sunlight that reaches the ice interior. Winds compress mobile flows and push them into ridges where rafting and pressure thrust slabs atop one another, creating keels that reach far below the mean underside and sails that rise above the surface. These deformations thicken local patches of the cover well beyond their thermodynamic thickness and introduce heterogeneity that matters for light transmission habitat and mechanical strength. Leads and polinias, the recurring openings in the cover, play an outsized role in the exchange of heat and gases. Leads formed by wind stress and shear expose dark water to cold air, allowing intense heat loss and rapid new ice formation. The resulting brine injection can pump dense water into the ocean interior. Coastal polynyas sustained by persistent offshore winds or by currents that spread new ice away from capes and bay mouths act as production lines for thin ice and as winter chimneys for atmospheric cooling. Where tidal flexure currents or upwelling keep water close to the freezing point against the underside of the cover, small zones remain thinner than their surroundings and permit more light to pass into the upper ocean. Even under low solar elevation, scattering within snow grains and ice crystals allows a diffuse glow to penetrate a few decimeters into the top of the cover, and where the cover is thin and clear, that transmission can support a narrow belt of photosynthesis within or just beneath the ice. The brine channel network provides microhabitats in which microbes endure by exploiting the slow, steady fluxes of dissolved nutrients and by adjusting to high salt and cold. Under a cover that thickens toward meters or more, the upper ocean's mixed layer cools and stabilizes, and the exchange of carbon dioxide and oxygen with the atmosphere becomes episodic, concentrated into brief seasons and narrow openings. This throttling favors a tendency toward lower oxygen in deeper layers if organic matter continues to sink while the surface layers become prone to transient supersaturation and undersaturation events as leads open and close. The mechanical behavior of the cover governs how readily it can fracture under wind and current stress. A thin, newly formed skin fractures easily and moves with the wind, producing long linear leads that heal and reopen repeatedly. A thick multi-year cover resists motion as a consolidated plate and transfers stress to a few large faults and pressure zones, producing wide ridged belts that can anchor the pack against coastlines and shoals. Where shelves are wide, the margin of grounded ice that flows from land into the sea can expand and push a floating ice shelf outward. Beneath such a shelf, cold salty water formed in nearby polynyas can intrude, melt the base mix with meltwater to form buoyant plumes, and rise to ventilate the underside and the shelf front. If those exchanges weaken, and the undershelf cavity fills with very cold, relatively fresh water, basal melt slows and the shelf thickens, stiffening the coastal fringe of the pack. The interplay between ocean heat flux and ice strength becomes decisive for whether a seasonal opening can recur in the same place. Tides and internal waves stir heat upward from a few tens of meters depth and can slow ice growth without entirely preventing it. Geothermal heat enters from below the abyss at a small rate everywhere and can be concentrated locally by hydrothermal circulation through young crust. While modest compared to winter atmospheric losses, this bottom source matters over long intervals when the lid remains in place. The large-scale structure of the ocean beneath sea ice is a stacked arrangement, a cold, relatively fresh surface layer set to the freezing point by contact with the ice, a jump in salinity and density across the halocline, and a deeper reservoir whose temperature and nutrient content reflect where and how it last contacted the surface. If brine rejection is vigorous and leads are common, deep waters can be regularly renewed and kept close to the freezing point. If the cover is more continuous and fresh water capping persists through summers, deep waters can become isolated and heat can accumulate slowly without reaching the surface for many years. This isolation protects the underside of the cover from immediate erosion by short warm episodes and gives the ice-ocean system memory. Light that does pass into the water column is absorbed primarily by the uppermost meter, when plankton or particles are present, and can reach a few meters under very clear conditions. In regions where shelves extend into low latitudes, the sun at high angle during certain seasons can deliver enough light through thin snow and ice to allow a narrow pulse of primary production, especially where tidal cracks or shear zones create skylights. Nutrients resupplied by winter mixing or by upwelling along grounded keels feed brief blooms that export small amounts of carbon to depth and return some oxygen to surface waters. In thicker snow-covered belts, photosynthesis dwindles, and microbial processes pivot toward the slow recycling of organic matter within brine networks and at the ice-water interface. The acoustics and mechanics of a frozen sea also alter how storms impart energy. Where the cover is continuous, waves from distant storms are damped by flexure and friction over the first few tens of kilometers, so the interior pack feels less stirring and retains a smoother underside. At the margins, wave fracture can break the cover into flows and create a zone of pancake ice that grows by collisions and freezing of slush, then consolidates as the sea calms. This marginal ice zone is a dynamic factory for new ice, and a gate for heat exchange, and its width determines how far storms can work their way into the pack to create openings. The state of the sea ice thus controls and is controlled by the ocean's mixed layer, by salinity stratification, by the rhythm of openings that vent heat and gases, and by the thin ecological skins that persist within brine and under skylights. In settings consistent with low-latitude ice advance, these processes concentrate exchanges into narrow features and short seasons, leading to a surface ocean that lives much of the year at the freezing point, and a deeper ocean whose renewal depends on how often and how intensely salt is rejected into it. The picture is neither a uniformly sealed ocean nor a permanently open one, but a shifting mosaic of thickness, fractures, ridges, and recurring openings that together mediate the planet's ability to store heat in the sea and to insulate it from the air while offering isolated refuges where light liquid water and nutrients still meet. Evidence from rocks and minerals records what an icy world does to landscapes, coastlines, and seas, and during cryogeny and glaciation, several signatures recur in many regions and allow a coherent picture of conditions to take shape. At the most direct level, sediments derive from ice show traits that moving ice imparts to fragments it carries and to the beds it passes over. A common rock is called diamictite, a poorly sorted mixture in which pebbles and boulders float in a muddy to sandy matrix. When such diamictite rests on a bed that bears grooves and scratches that run in a common direction, the contact records abrasion by stones frozen into a glacier's base. These grooves are called striations, and the polished bed beneath is called a glacial pavement. Clasts within the diamictite often show facets and sharp edges where grinding round some corners, while leaving others plainer a texture typical of pieces knocked together beneath ice. In some basins, finely layered muds accumulate in quiet water, and then show isolated outsized stones that fall into them and deform the laminae into soft bowls and draped wings. Such outsized stones are called drop stones when they fall from floating ice. Where the surrounding sediment is a marine silt or a finely laminated clay, the outsized fragment can be traced to a different source rock than the basin walls, and the layers beneath it sag, while layers above are draped a mechanical sign of delivery from a raft rather than from a river channel. In shelves close to ice margins, mass flows triggered by slope failure mix coarse and fine particles and produce chaotic beds with torn blocks. Yet even there, lone stones aligned with overlying fine laminae point to ice rafting as a supplement to gravity flows. In many sequences, the glacial units extend to very low paleolatitudes. The angle at which a rock's preserved magnetization points into or out of the Earth, called its inclination, can be used to estimate the latitude at which magnetic minerals last cooled or were last deposited and locked in a field. when fine sediments settle or lava cools, small iron-bearing grains align with the field and acquire a remnant magnetization. Later heating or alteration can reset that signal, so careful work is needed to isolate the original component. When the primary component in glacial units and interbedded volcanic flows points to low inclinations, and when field tests show that the magnetization predates tilting and burial, the simplest reading is that ice reached near the equator during deposition. The presence of glacial features in rocks with these low-latitude signals supports the view that either sea ice and glaciers extended far into the tropics, or that cold ocean conditions coexisted with belts of open water very near the equator. Within the thick successions that mark long glaciations, chemistry of the ocean also leaves distinct layers. Iron-rich bands called banded iron formations reappear in the cryogenian after being rare for long stretches of Proterozoic time. These rocks consist of repeated thin layers of iron minerals and silica, and form when iron that is dissolved in an oxygen-poor deep ocean reaches sites where oxidation and precipitation occur. Under a wide ice cover, exchange of oxygen with the air is limited, and deep waters can become oxygen-poor while iron released from hydrothermal vents and from the alteration of basalt accumulates. Where the water column rises or mixes to shoaler depths, or where photosynthesis beneath thin ice leaks oxygen into a narrow zone dissolved, iron oxidizes and falls out as iron oxides and hydroxides, creating layers that alternate with silica-rich laminae. The return of such iron-rich layers in cryogenian basins is consistent with a deep ocean that is more isolated from the air than in warm times, and with episodic pulses of oxidation that mark points of contact between deep stores and shallower, more oxygenated layers. Additional geochemical traces sit within the glacial sediments and in thin carbonates that accumulate in pauses during the cold intervals. The ratio of carbon-13 to carbon-12 in carbonate minerals reported as carbon isotope values varies with the balance between organic burial and total carbonate precipitation in the ocean. During parts of the glaciations, these values swing toward negative excursions, which indicates either a change in the isotopic composition of the dissolved inorganic carbon pool or unusual mixing of sources, because burial of organic matter tends to raise the ratio in the residual seawater. A fall can reflect reduced burial addition of carbon with light isotope signature from respiration of organic matter or mixing with fluids that hold light carbon. In the cold ocean capped by ice low oxygen, waters can accumulate respiratory carbon at depth, and when that carbon contact sites of carbonate formation during short ice retreats or beneath thin covers, the resulting minerals inherit more negative values. Sulfur isotopes tell related stories about the cycling of sulfur through sulfate reduction in anoxic settings and reoxidation in zones that receive a little oxygen. Pyrite, the iron sulfide that forms where microbes reduce sulfate to sulfide, is abundant in some cryogenian marine sediments, and often shows signals that point to extensive microbial processing under oxygen-poor waters. Together, these isotopic lines align with the physical picture of a stratified ocean with limited ventilation, and one in which short pulses of mixing punctuate long intervals of separation. In nearshore and continental settings, tills and diamictites rest directly on weathered bedrock, and the contact shows sharp truncation of older soils. Boulder pavements with clasts pushed into soft underlying clay demonstrate the passage of grounded ice over water-rich substrates. Where glaciers reach the sea and become floating tongues, the transition leaves a sequence that begins with subglacial tills, passes upward into stratified sands and silts deposited by meltwater, and then into marine mudstone with scattered loam stones, a vertical arrangement that captures ice advance from land to sea. In tropical carbonate platforms whose normal products are lime muds built by microbial mats and carbonate sands moved by waves, the arrival of cold conditions introduces lenses of dolostone and marl with drop stones and eroded surfaces that interrupt the usual shallow warm water factories. In deeper parts of basins, the laminae that mark quiet deposition are commonly disturbed by soft sediment deformation tied to ice rafting and by pulses of current driven by density flows that pour off glaciated shelves. A distinctive mechanical feature appears in many successions, striated clasts embedded in fine matrices that show no rounding, by long transport implying short movement within ice rather than extended river travel. Some of these clasts carry overprinted microfractures filled with quartz and calcite that formed when freezing and thawing stressed the stone before it came to rest. The arrangement of sequences over large regions shows repeated cycles of grounded ice presence and marine influence, with intervening intervals of fine deposition under reduced energy. That alternation fits a frozen sea that moves and breathes through openings and advances and retreats at its margins without losing its broad reach. In sum, the combined record of diamictites with glacial fabrics, lone stones that deform quiet water laminae striated and faceted clasts, low-latitude paleomagnetic inclinations preserved in interbedded units, reappearance of iron-rich chemical layers that require oxygen, poor deep waters with episodic oxidation, and isotope patterns in carbon and sulfur that track altered ventilation all point to prolonged cold conditions under which ice masses meet the sea at many latitudes and a stratified ocean, exchanges heat and gases through limited windows. The rocks do not simply record cool weather, they record a state in which ice is a major agent of erosion and transport on land, and a recurrent raft for debris at sea, while the chemistry of deep waters and the mode of sedimentation respond to a lid that narrows the pathways between air and ocean without closing them entirely. When ice spreads across continents and the sea, the balance of gases in the air evolves under a new set of surface rules. The key change is a broad suppression of silicate weathering on land, the suite of reactions by which rain and soil waters consume carbon dioxide and carry calcium and magnesium to the ocean. With bedrock buried beneath ice sheets or mantled by thin frozen soils, liquid water cannot reach mineral surfaces for much of the year, and in many places for many years in a row. Rivers shrink or cease, and the conveyor that normally pulls carbon from the sky slows to a crawl. The same cooling that builds ice also dries the air in many belts, because cold air holds less water vapor, and weaker evaporation reduces cloud supply over frozen seas. Less rainfall means less chemical attack, even where rock remains exposed. In such conditions, the deep sources of carbon dioxide steady on human scales and slowly varying on geologic scales continue. Volcanic vents at arcs and hotspots diffuse emissions across faulted ground, and metamorphic breakdown of carbonates in thickened crust each add carbon dioxide to the atmosphere at rates set by plate motion and heat flow rather than by weather. Because removal is throttled while supply persists, the concentration of carbon dioxide in air trends upward over spans long compared to seasons and short compared to the age of continents. The atmosphere under widespread ice behaves differently from a warm sky. Water vapor is scarce in the cold troposphere, so the fast positive feedback that water vapor provides in warm climates is muted. With fewer clouds in some belts and more low clouds in others, the radiative structure shifts in ways that depend on where open water remains and where cold surfaces dominate. Over bright snow and sea ice, additional low cloud may reflect little extra sunlight because the surface is already reflective, while high thin cloud still adds a small greenhouse effect by trapping infrared energy that the surface and lower air emit. Aloft, the stratosphere cools as greenhouse gases increase, a response set by the way these gases radiate heat to space at high altitude. Colder stratospheric temperatures alter ozone chemistry and can change how long particles and trace gases linger. At the same time, reduced convection from a cold surface lowers the upward transport of water vapor, which shortens the chain of reactions that destroy methane in the lower stratosphere. Yet the overall lifetime of methane still depends strongly on the presence of oxygen and on the ultraviolet light that drives oxidation. In the late Proterozoic, oxygen stands at appreciable levels, so methane released from wetlands along unfrozen margins or from anoxic niches beneath sea ice meets an oxidizing sky and is removed on timescales of years to decades. The net result is that methane remains a minor and short-lived component compared to carbon dioxide during extended cold. The nitrogen cycle responds to the altered ocean as well. Where deep waters are oxygen poor and stratified beneath a stable lid, microbes convert nitrate to nitrogen gas in the absence of oxygen, a process that can raise the flux of nitrous oxide, another greenhouse gas. Yet the same isolation that promotes anoxia also restricts gas exchange with the atmosphere to brief episodes at Leads and Polynias, and cold salty brines carry many gases downward when new ice forms. These throttles make it difficult for short-lived trace gases to accumulate to levels that dominate radiative balance. Carbon dioxide, with its long lifetime and well-mixed distribution, becomes the principal variable term in the atmospheric inventory as weathering wanes. Aerosols add further texture to the cold sky. Explosive volcanic eruptions inject sulfur into the stratosphere, where it forms sulfate particles that reflect sunlight and cool the surface for a few years per large event. In a persistently icy state, such pulses ride atop a background defined by high albedo and weak water vapor. Their cooling is real but transient, and the particles fall out long before the slow, deep sources of carbon dioxide vary appreciably. Over deserts that expand along subtropics, and over deglaciated outwash plains around ice margins, wind lifts mineral dust that can brighten cloud tops and scatter sunlight. Dust also falls on snowfields and sea ice. Where the dust load is heavy, the settled grains darken the surface and lower albedo. Where snow remains clean because sources are distant and moisture transport is weak, the bright surface persists. The sign of the dust effect thus depends on where particles travel and land, but the controlling fact for the atmosphere is that the supply and removal of aerosol are tied to winds and storms, not to the slow chemistry that governs carbon exchange between rock and air. The hydrologic cycle weakens across large areas as evaporation falls and sea ice blocks fluxes. This reduces the rate at which carbonic acid forms in soils and diminishes the wash of bicarbonate to the sea. At the same time, salt rejected during sea ice growth sinks and ventilates the uppermost deep ocean. But away from recurring openings, the contact between surface and depth is scant. Limited contact slows the return of dissolved inorganic carbon from deep to shallow waters and narrows the strip of sea surface through which the ocean breathes with the air. The atmosphere, thin compared to the oceanic carbon pool but quick to equilibrate with small fluxes, responds more to changes in land weathering than to these oceanic throttles during long cold spells. On time horizons of hundreds of thousands of years, the curve of atmospheric carbon dioxide becomes the integral of the mismatch between supply and removal. Where ice buries the most reactive terrains and runoff dwindles, the mismatch is positive and grows. On shorter horizons, seasons and decades imprint only small oscillations on the larger climb. This slow rise coexists with a surface energy budget dominated by reflection from ice and snow. and by modest downwelling infrared radiation from a dry cold air column. The atmosphere's circulation under these constraints shows sharpened jets and expanded zones of subsidence where cold, heavy air drains from ice domes. Strong surface temperature contrasts at ice margins sharpen baroclinic zones that steer storms, while the thinness of the mixed layer beneath sea ice mutes the feedback from ocean heat. Release on storm strength. The troposphere remains shallow over the cold interior of ice sheets, and deeper over the few areas of open water that survive focusing, cloud-making processes over leads and swelling cloud decks in narrow corridors rather than across entire basins. Trace reactive gases adjust to this structure. Oxidants remain sufficient to scrub methane. Carbon monoxide from volcanic and hydrothermal sources oxidizes and contributes to carbon dioxide. Halogens released from salty frost flowers on new sea ice can participate in ozone chemistry near the surface, but their influence remains local and seasonal. Throughout, the largest lever that the atmosphere holds is the inventory of carbon dioxide, and the largest constraint on that lever under ice is the curtailed capacity of land to consume it. The outcome is a sky that dries clears in some regions and thickens in others, cools aloft as greenhouse gases increase, and accumulates carbon dioxide slowly as long as deep sources outpace weathering sinks. The picture is not one of abrupt swings dictated by the air alone, but of a patient adjustment in which the atmosphere integrates the imbalance created at the surface when ice removes the pathways that ordinarily draw carbon from the air and deliver it to the ocean. In this state, the composition and structure of the sky become a ledger of that imbalance, written in higher carbon dioxide, lower water, vapor-altered clouds, and a circulation guided by bright, cold continents, and a lid over the sea. As the cold world persists and land weathering remains weak, carbon dioxide from deep Earth supplies accumulates in the air until the infrared trapping it provides grows strong enough to challenge the bright surface. The source is steady on human timescales and slow on geologic ones, yet in the absence of efficient sinks the excess mounts. Each year, small additions from volcanic vents, hot springs and metamorphic devolatilization mix through the atmosphere and dissolve into the surface ocean at Leeds and Polinias. But the lid of ice and the dryness of the sky keep most of the increment in the air. The radiative effect of carbon dioxide follows simple physics. Molecules absorb and emit infrared radiation in particular bands. As concentration rises, the central parts of those bands saturate, yet the edges broadened by pressure and temperature continue to admit more absorption, and the altitude at which the air can radiate to space moves upward to colder levels. Colder levels emit less thermal energy, so the planet loses heat more slowly, and the surface and lower air must warm until a new balance is found between incoming sunlight and outgoing infrared. Under a bright, icy surface, sunlight absorbed is small, so a large greenhouse strength is needed to lift emissions sufficiently. The period of accumulation can last for many hundreds of thousands of years because the atmosphere integrates a small positive imbalance between deep sources and suppressed weathering sinks. During this climb, the infrared structure of the sky changes in a way that strengthens lower tropospheric temperature, despite the planet's overall high reflectivity. Water vapor remains scarce over the cold interior of ice sheets and over thick sea ice, but at the margins, especially in belts of recurring openings, warming from added greenhouse gases raises humidity enough to allow a local amplification. The additional water vapor increases downwelling infrared radiation in these corridors and slows nighttime cooling, which helps seasonal openings persist longer and widen earlier each year. The ocean beneath the cover stores a backlog of heat in its deeper layers where brine rejection is weak and mixing rare. When greenhouse strengthening delivers slightly warmer summers and longer seasons of open water around the margins, wind and waves inject more energy into the upper ocean, and a thin layer of open water forms and absorbs sunlight that the nearby ice would have reflected. The extra heat in this dark patch prevents early autumn freeze and delays the onset of winter thickening, creating a carryover that slightly increases the starting temperature of the next year's surface layer. The change is incremental at first, but the sign is consistent. In landscapes where land ice reaches lower elevations, rising greenhouse forcing weakens summer snow persistence and lowers the accumulation area of glaciers. The response lags because thick ice sheets carry large thermal inertia, but the edges become more prone to seasonal meltwater that darkens the surface, lowers albedo locally, and allows solar energy to penetrate deeper into the snow and fern. Melt ponds on bare ice concentrate light and accelerate local ablation. In seas with wide shelves, the transition takes shape as an expansion of seasonal polynyas that remain open late into autumn and appear earlier in spring. At some point, the integrated greenhouse forcing crosses a threshold at which the season of open water becomes long enough to reverse the previous balance. Dark water exposed during high sun absorbs more energy than winter can return to the air through the new cover before the next spring breakup. When this occurs across broad regions rather than at scattered leads, the system crosses from perennial to seasonal ice, and the ice albedo feedback flip sign. Retreat then becomes self-supporting. As more open water forms in summer, more heat is taken up, and the next year a still larger area resists freeze. Winds accelerate the transition by tearing apart thinning flows, pushing them into ridges that leave wide patches of open water between them and exporting broken ice out of formation zones. Ocean currents carry heat released in one opening to weaken ice downstream, while tidal mixing raises warmer subsurface layers toward the underside of the pack in straits and over sills. The earliest large retreats are likely to occur where insulation is highest and where ice is thinnest, which in cryogenian arrangements means low latitude shelves and marginal seas that lie beneath strong sunlight. As coverage shrinks, the planetary albedo decreases. The same incoming sunlight now finds more dark targets and fewer bright ones, so the fraction absorbed by the surface rises. The atmosphere responds quickly to the additional surface heat through turbulent exchange, and the lapse rate steepens over open water compared to the flat, cold profile above ice. Low clouds that once brighten the planet above ice become less frequent over warm open water in summer, because humidity profiles and stability change, and broken cumulus fields admit more sunlight to the sea surface between them. Because the greenhouse effect from carbon dioxide is well mixed globally, the regional albedo changes at low latitudes carry global consequences for the energy budget, and the drop-in reflectivity accelerates the warming begun by gas accumulation. In mountain belts and on continental domes, the rise in summer energy at the surface begins to push the snowline upslope. Glaciers thin and their lower tongues retreat. As ice pulls back from the sea in embayments, the contact between ocean and atmosphere enlarges and exchanges speed up. Carbon dioxide in the air begins to flow into the water over longer seasons and into a thicker surface layer. Yet on the timescale of the initial retreat, the atmospheric inventory remains high, because the global weathering engine on land is still largely dormant beneath ice. The onset of deglaciation therefore does not immediately draw down the greenhouse reservoir that built it. Instead, warming proceeds until the combined effects of darkened surfaces and continued high carbon dioxide push seasonal conditions well across the melting threshold. The mechanical breakup of pack ice matters here because a fragmented cover presents a larger perimeter, along which waves can act, and along which heat and moisture fluxes concentrate. As storms travel along sharper baroclinic zones that form at the ice edge, their winds fracture new openings that lengthen fetch for waves and wave energy, then penetrates deeper into the remaining pack to flex and weaken flows. Once late spring and early summer find large swathes of low-latitude ocean, exposed the rate of change jumps because solar input is then largest. The ocean's mixed layer warms rapidly, and the halocline weakens as meltwater is stirred and as saltier water from depth rises. With the halocline eroded, heat stored below reaches the surface more readily and contributes to further thinning. In some basins, upwelling driven by winds along the retreating edge brings nutrient-rich water to the surface and allows brief blooms that darken the sea and absorb more sunlight. In others, clear water admits light deeper and warms a thicker layer. Both routes work toward the same end of raising ocean heat content and delaying the return of winter ice. The air over these widening openings grows warmer and moister through summer, and downwelling infrared radiation from water vapor increases, compensating for nighttime cooling and for transient cloud shading. Rain on remaining snow further reduces its reflectivity by changing grain size and by adding liquid water that improves absorption. The pace of retreat is not uniform across the globe because geography, winds and currents vary. But once the global albedo falls past a critical fraction, the energy gain becomes a planetary property that no local rebound can offset. A world that had needed a very high carbon dioxide level to challenge bright ice finds that the same level now drives a pronounced excess of absorbed energy. In that condition, the boundary between ice and water migrates poleward and to higher elevations year after year, until only the coldest regions still sustain summer snow. The deep ocean, long isolated in places, then begins to feel the pull of a more vigorous surface exchange as leads coalesce into open seas and as winter convection recovers, where brine rejection remains strong. Yet the defining mark of onset is simpler. Rising greenhouse strength under a muted weathering sink tips the energy budget toward the warm side. The sea sheds its perennial cover in belts, where sunlight is strongest. The albedo decrease flips the major feedback from positive in cooling to positive in warming, and the planet commits to a broad retreat of ice. The broad features of physics and chemistry fix this path. Carbon dioxide accumulates when weathering is throttled. Infrared trapping strengthens seasonal open water, takes root, and widens dark surfaces absorb more sunlight, and the balance crosses the line at which winter can no longer rebuild what summer removes. When bright ice yields to widening dark seas and the balance turns to warming, the planet enters an aftermath shaped by a strong greenhouse sky and a landscape newly freed from its lid. Carbon dioxide stands high because the long winter of the weak weathering has allowed deep sources to fill the air. With the reflective cover receding, the same greenhouse strength that once worked just to challenge ice now drives a large excess of absorbed energy. Summers grow long and warm even at middle, and some low latitudes that had carried sea ice and humid air spreads inland from coasts over ground that was recently ground by moving ice or buried beneath it. Fresh mineral surfaces are abundant where glaciers retreated and where shelves that had held grounded ice now lie below rising seas. Rain falls on this new terrain and on weathered belts beside it, and chemical reactions accelerate. Silicate minerals take up carbon dioxide in waters that carry carbonic acid, and the release of calcium and magnesium into rivers climbs sharply. Streams run charged with bicarbonate and deliver large loads of alkalinity to coastal seas. At the same time, sea level rises as land ice melts, flooding broad shelves that had been near the surface and creating large areas of shallow, sunlit water above beds of freshly reworked sediment. In these settings, the chemistry of seawater slides toward oversaturation with respect to carbonate minerals because alkalinity from rivers is high, and because the exchange with a high carbon dioxide atmosphere drives the dissolved inorganic carbon pool to large values. Where the combination of temperature, alkalinity, and calcium activity permits, carbonate mud precipitates rapidly from seawater or within thin films and microenvironments on and just below the sediment surface. The result is a distinctive blanket of carbonate that rests directly on glacial deposits across many basins. These deposits are called cap carbonates because they sit as a cap above diamictites, tills, and dropstone-rich muds that record ice. The cap beds are commonly thin compared to the great thickness of the glacial successions they cover, yet they are laterally extensive and show sedimentary features that point to rapid growth in shallow water, fed by unusual chemistry. Laminae are even, and continuous over long distances ripple marks are present, where waves touch the bottom, and at times fabrics record the former presence of crystal fans that grew at or just beneath the seabed. Those fans are often replaced by dolomite in the rock record, but their shapes speak to early fast mineral growth in pore waters and at the interface where seawater met sediment. Sheets of carbonate cement can fill cracks that opened in soft sediment as gas escaped, or as early cements expanded and teepee-like buckling can appear where shrinkage and expansion alternated. Tubular cavities and sheeted voids may reflect degassing or decay of organic films during cementation in a water column and seabed that received a surge of reactive ions. The light-stable isotope of carbon tends to be enriched in these cap carbonates compared to typical warm shelf deposits, and the measured ratios often show pronounced negative values at the base that recover upward. This pattern is consistent with a dissolved carbon pool influenced by large inputs of carbon from the atmosphere and from deep ocean waters that had accumulated respiratory carbon under isolation during the cold interval. As overturn strengthens during deglaciation, and as mixing connects shallow and deep layers, that deep store can contact the surface and share its light isotope signature. With time, as weathering on land continues to accelerate, and as burial of carbonate proceeds, the isotopic composition can drift back toward typical values for open shelf deposition. The sulfur system also carries marks of the aftermath. Rivers bring sulfate from the oxidation of sulfides that were exposed during glacial erosion and from weathering of uplifted belts. In oxygen, pour pockets that linger on shelves and in basins. As circulation catches up with geometric change, microbes reduce sulfate and produce sulfide that combines with iron to form pyrite. As circulation strengthens and oxygen returns to a larger share of the water column, reoxidation of sulfide increases and sulfate accumulates in the ocean. The shifting balance among reduction, burial, and reoxidation leaves its signature in sulfur isotope ratios in both pyrite and sulfate minerals in and above the cap. The physical environment that hosts cap carbonate formation is one of strong seasonality and vigorous exchange. Storms pass along the new ice edge and over warm shallow seas that have replaced frozen shelves, and their winds stir bottom sediments into suspension. On some coasts, river plumes deliver suspended clays and silt that settle through carbonate-rich waters and mingle with crystals growing at the seabed. On other coasts, clear water allows light to penetrate and heat to build in the uppermost meter, while minerals accrete below. In either case, the high alkalinity of the sea and the supersaturation of pore waters favour quick precipitation. Because carbonate mud stiffens quickly with early cement delicate laminae, and ripples can be preserved without being destroyed by waves and burrowing, which may be sparse immediately after ice retreat. The thickness of cap carbonates varies because accommodation space and supply differ from shelf to shelf, and because local currents and waves winnow fine material. Where topography funnels, tidal flow dunes and bars of carbonate sand can form above a smooth base of laminated mud. Where topography is flat and floodplains extend far inland, the cap can be a simple, even sheet across a broad region. The rapid chemical drawdown of carbon dioxide by enhanced weathering does not occur in a moment. It takes many tens to hundreds of thousands of years for the thermostat of silicate weathering to answer the high greenhouse and the high runoff with enough removal to cut the atmospheric reservoir. During this interval, the climate remains warm and humid. Across wide belts, ice continues to retreat toward higher latitudes and elevations, and the cap factory of shallow seas remains active. As land surfaces stabilize under soils and as vegetation-free weathering slows from its initial pulse to an elevated but steadier rate, the rivers that had carried extraordinary loads of alkalinity begin to carry less, and the degree of oversaturation on shelves falls. Carbonate precipitation then shifts toward the more familiar balance between biological and abiotic processes, and toward rates that allow burrowing and wave stirring to keep pace with accumulation. The upper contact of cap carbonates grades into ordinary platform and ramp deposits that reflect this return to typical chemistry and ecology for a warm period. During the super greenhouse interval, the hydrologic cycle is strong. Evaporation over warm seas and intense rainfall over hot land produce large freshwater fluxes that alter salinity near coasts and drive buoyant plumes along the shoreline. These plumes can trap heat and aid carbonate precipitation by capping seawater enriched in calcium and bicarbonate with a warm, less dense layer. The same cycle accelerates physical erosion and supplies abundant terrigenous sediment that mixes with or overlays the cap in deltas and fans where rivers deliver their loads, in far-field deep basins that have been isolated under ice bottom. Waters warm slowly, and stratification weakens as wind stress and tidal mixing gain reach over ice-free surfaces. Oxygen penetrates. Organic matter that had accumulated under anoxic conditions is oxidized, and the dissolved iron that had fed banded iron formation ceases to build up. The geochemical switch from iron deposition to carbonate blankets in many basins is thus a natural outcome of changing ventilation and chemistry as the lid lifts. The visual juxtaposition in Outcrop tells the same story in a simple way. A sharp, often erosional surface truncates diamictite or glacially influenced mudstone, and above it lies a crisp package of pale grey to buff carbonate with smooth lamination. Ripple cross, lamination crystal fan relics and early cemented cracks. That contrast records the energy switch from a cold world with sea ice and debris-laden rafts to a warm, chemically charged sea that turns dissolved carbon and cations into rock. As carbon dioxide continues to be removed by weathering and by carbonate burial, its atmospheric concentration begins to fall from its peak, and the greenhouse excess narrows. Yet within the span of cap carbonate deposition, the dominant features remain strong: warmth high, runoff high alkalinity, rapid carbonate precipitation in shallow waters, and a geochemical imprint of mixing between deep light carbon-rich stores and surface waters, newly connected to a sky that still holds abundant carbon dioxide. A frozen planet need not be uniform, and the rock record, together with physical reasoning, points to strong spatial variability during cryogeny and glaciation, including the possibility that belts or recurrent corridors of open water persist within a dominantly ice-covered ocean. Variability begins with geography. Low-latitude continents with broad shelves create long coastlines where winds accelerate, tides focus, and polynyas recur, while interior basins at higher elevations remain locked beneath cold-based ice that preserves striated pavements and plucked bedrock. Along some margins, indicators of wet-based glaciation appear, such as streamlined drumlin fields and deformed tills, which require sliding at the glacier base, and the presence of meltwater under pressure. Basal meltwater can arise from frictional heating beneath fast-flowing ice, from geothermal flux concentrated by thick covers, or from pressure melting at rough beds. Its presence implies thermal regimes that differ across short distances, cold-based frozen, to the bed plateaus grade downslope into wet-based tongues, where the ice accelerates and delivers debris to marine forelands. At those forelands, stacked sequences show subglacial diamictite overlain by stratified sands and silts, deposited by meltwater, then by mudstone with loanstones interpreted as ice-rafted debris. The vertical order records grounded ice retreat to a floating margin and persistent rafting rather than a single static lid. In tropical settings, some successions include wave ripples, hummocky cross-stratification, and erosional scours interbedded with glacially influenced layers. These features form under oscillatory flows produced by storms in water shallow enough for waves to touch the bottom, so their presence inside glacial packages is consistent with nearby open water during at least some seasons. Likewise, delicate lamination in fine muds adjacent to horizons with dropstone suggests alternating quiet settling under a cover with episodic delivery of clasts from drifting ice, a rhythm more natural for seas with leads and widening openings than for a fully sealed surface. On shelves now known to have lain near the equator, carbonate platforms record breaks in warm factory conditions, replaced by thin dollostones with loanstones, and by marls that carry microtextures of rapid cementation. Some of these intervals include ripple fields and cross-lamination sets, indicative of sustained bottom flows, again pointing to times and places where a local fetch of open water allowed waves to act. The ocean under an ice cover also supports heterogeneity in thickness governed by wind stress currents and tides. Ridges with deep keels alternate with thin refrozen leads, and coastal polynyas persist where winds drive ice away from capes and embayments. Over sills and in straits, tidal mixing lifts warmer subsurface water and locally thins the cover, producing skylights that recur in phase with tides and maintain convective chimneys during winter. Where volcanic islands pierce the cover, or where basaltic ridges lie just below the surface, geothermal and advective heat flux can keep compact openings. Such features concentrate gas exchange, moisture flux, and snowfall, and their footprints can migrate or cluster according to winds fixed by continental outlines. A sloping halocline reinforces spatial contrast by impeding upward heat transport in quiescent interiors, while allowing heat to reach the surface in shear zones and along boundaries where the lid is thin. In these settings, bands of thinner ice can align with prevailing wind belts and produce quasi-zonal corridors that act as seasonally recurring water belts, even if the annual mean coverage remains extensive. The possibility of equatorial belts arises naturally in worlds with strong sunlight at low latitude and with large land area in the tropics. During summers, thin snow and ice in those belts absorb more energy per square meter than at high latitudes, and slight differences in thickness between neighbouring regions can decide whether a patch crosses the melt threshold. Once a patch melts to open water, the local albedo collapses heat, uptake jumps, and the area resists refreezing until late in the season, a behaviour that can repeat annually even while nearby regions remain under perennial ice. The signature of such belts would be mixed, marine and glacial facies at low paleolatitudes, with evidence of ice rafting interleaved with wave-worked beds, and with currents strong enough to build ripples and scours. Reports of wet-based glacial fabrics at low latitude add a terrestrial complement sliding ice that either terminates in water or advances across saturated coastal plains, both scenarios that welcome seasonal melting and liquid pathways even under a cold sky. Spatial variability extends to chemistry. Where openings recur, oxygen enters the upper ocean and oxidizes reduced species that have accumulated in the halocline. Short pulses of oxidation in these corridors can precipitate thin iron-rich layers that alternate with quiet water muds, while basins far from openings retain oxygen, poor deep waters and different mineral stacks. Carbon isotope patterns can vary laterally as well, if regions under thin covers assimilate deep light carbon-rich waters during seasonal upwelling, while isolated interiors do not. Dust deposition likely shows belts and plumes tied to subtropical dry zones over continents. Where such plumes pass over open leads, they may brighten clouds and suppress shortwave absorption, but where they settle onto snow, they can darken it. The distribution of these outcomes is not uniform and depends on storm tracks locked to continental positions. Sea ice mobility further sharpens contrasts. Export pathways that funnel flows through straits and along coasts build thick ridged barriers downstream and extended areas of thin young ice upstream, arranging mosaics that persist for years. The mechanics of fracture also organize space, linear kinematic features, shear zones several kilometers wide, serve as perennial lines of weakness that preferentially open during wind shifts and tidal cycles. Their existence makes repeated openings more likely in the same bands. Within this framework, the extremes of a hard snowball and a slush ball are end members of a spectrum one, with a nearly continuous thick cover that leaves only small volcanic or tidal skylights, and another with organised belts of seasonal open water in the sunniest latitudes and in wind-reinforced corridors. The rock record cannot count the fraction of open water directly, but its combination of storm wave structures within glacier marine packages, wet-based indicators at low latitude interbedded chemical and clastic layers that demand intermittent ventilation, and lateral faces changes over short distances all support large spatial contrasts. Physical models with realistic winds and tides under Neoproterozoic geography achieve similar patterns with meters to many meters thick, mean ice punctuated by thinner bands and recurring polynyas where stirring and heat flux suffice. These patterns allow heat and gases to breathe in and out through narrow gates, while leaving the global energy budget dominated by high albedo. They also define where sediment is delivered, where currents scour, and where carbonate or iron-rich laminae form, imprinting the variability onto outcrops that now sit on separate continents. The emerging picture is that prolonged cryogenian cold includes wide regions of persistent ice, yet allows organised belts and recurring windows of open water and thin cover that track geography, winds and tides, and that these features explain the juxtaposition of glacial textures with wave-worked beds and the patchwork geochemistry observed across basins that all share the same cold interval. Time is a central dimension of cryogenian glaciation, and the rock record tied to robust age markers allows a picture of pacing that distinguishes a long Sturtian episode from a shorter Marinoan episode, while leaving room for regional variability and internal rhythms. The Sturtian begins in the later Neoproterozoic around the early 700s of millions of years before the present, and persists for many tens of millions of years, long enough for thick stacks of diamictite, loamstone, rich mudstone, and iron-bearing chemical layers to accumulate on several continents. The Marinoan follows after an interglacial interval, and endures for low tens of millions of years, still long on geological scales, yet shorter than the Sturtian in most regions. Both glaciations terminate rapidly when warming overtakes high albedo, a contrast between very long residence in a cold state and a brief transition into the super greenhouse aftermath recorded by cap carbonates. Age control for these spans comes from radiometric dates on volcanic ash beds within, and bracketing the glacial successions from dates in interbedded lavas and sills, and from correlation of cap carbonate units that sit directly on glacial strata. Individual numbers vary from basin to basin, because some sequences preserve more datable layers than others, yet the combined evidence supports a Sturtian that lasts for several tens of millions of years, and a Marinoan that lasts for roughly an order of magnitude less time. Within these long envelopes, pacing appears in nested layers. The slowest layer is set by tectonics and the deep carbon cycle, which govern how long land weathering remains weak enough and greenhouse supply small enough for ice to persist. The next layer consists of advances and retreats of ice sheets and sea ice, on timescales from thousands to hundreds of thousands of years, paced by the position of snow lines, ocean heat content, and the geometry of marine margins. The fastest layer consists of seasonal to decadal breathing of Polynia's leads and thin ice belts that control moment-to-moment exchanges of heat and gases. Sedimentology preserves signatures of these layers. Thick Sturtian packages commonly show repeated motifs of subglacial tills, overlain by stratified meltwater sands and then by quiet water muds with loanstones, a vertical order that implies cycles of grounding flotation and ice rafting at marine margins. Sets of finely laminated muds interrupted by clusters of drop stones recur at intervals that suggest grouping into bundles consistent with orbital pacing, while storm-formed hummocky structures and wave ripples appear within otherwise glacial-marine stacks at low paleolatitudes, indicating episodic open water during some seasons. The Marinoan retains similar motifs, but often with fewer repeats, and thinner clastic totals consistent with a shorter residence time in the cold state. Geochemistry offers its own clocks. During long cold spans, deep waters isolated beneath thick sea ice become oxygen poor, and accumulate dissolved iron and isotopically light dissolved inorganic carbon. The reappearance of banded iron formations during parts of the Sturtian and locally during the Marinoan indicates prolonged intervals of poor ventilation punctuated by oxidation pulses when mixing events or seasonal openings reach depth. Carbon isotope records show sustained negative excursions within some glacial intervals, and especially sharp negative values at the base of cap carbonates, a pattern consistent with rapid release or upward mixing of carbon that had built up in isolated deep reservoirs, followed by progressive return toward more typical values as circulation and weathering re-established longer-term balances. The end of each ice age is fast compared to its life, in successions where volcanic units provide dates just below the upper glacial beds, and just above the lower cap carbonate the implied time between the last marine ice margin deposits and the onset of widespread carbonate precipitation is small relative to the duration of the glaciation itself. Physical reasoning aligns with this abruptness. Once greenhouse forcing from accumulated carbon dioxide pushes seasonal open water, to low latitudes dark surfaces absorb more sunlight than winter can remove the ice albedo feedback flip sign, and the retreat accelerates. Ocean heat stored beneath the halocline contributes to thinning once mixing increases and wave fracture of weakened flows grows openings rapidly. This shift from a bright to a dark planetary surface therefore occurs on timescales far shorter than those that held the cold state in place. Between the Sturtian and the Marinoan, an interglacial interval hosts volcanism rifting and sedimentation, that modify carbon sources in sinks and reshape gateways. Basaltic provinces emplaced in low latitudes create large swathes of reactive rock that later enhance silicate weathering when climate warms, and subsidence creates shelves that later collect glacial and cap units. Carbon isotope records in these intervening strata swing toward values that indicate altered balances between organic burial and carbonate precipitation, while microfossil evidence in some basins points to diversification among eukaryotes in surface waters. These developments unfold over millions of years and prepare a different starting geometry for the second glaciation. Inside each event, mechanical responses add their own tempo. As ice thickens on continents, the crust sinks and forebulges rise, shifting regional relative sea level and grounding lines over thousands to tens of thousands of years. Such isostatic adjustment can drive marine ice margins forward and backward without any large change in the global energy budget, imprinting cycles of grounding and flotation on shelf successions. During deglaciation, rebound lifts crust beneath retreating ice and modifies accommodation space for early carbonate deposition, influencing local thickness and texture of cap beds, while the overall rapidity of the switch remains. Atmospheric and oceanic circulation impart further rhythms. Orbital configurations that weaken high-latitude summers for extended intervals favor low accumulation of summer melt energy and allow snow to persist on uplands and wide coastal plains, reinforcing ice growth on timescales typical of precession and obliquity. Seaways and sills that focus tides and mixing generate repeatable bands of thin ice and recurring chimneys that ventilate the ocean, locally setting seasonal to decadal cycles of oxygenation and iron precipitation in specific corridors. Dust supply from subtropical belts waxes and wanes with aridity modulating cloud fields and the brightness of snow patches in ways that can add or subtract small amounts of energy on short timescales, while the long envelope remains fixed by greenhouse and albedo. The result is a hierarchy in which the Sturtian persists for many tens of millions of years under a stable cold equilibrium and ends quickly into widespread cap carbonate deposition, whereas the Marinoan persists for low tens of millions of years and also ends quickly with a similarly sharp chemical cap. Within both orbital scale cycles and mechanical adjustments shape the stacking of beds and the chemistry of deep waters, records long isolation punctuated by brief mixing. Compared at planetary scale, the two events share the same architecture of slow entry and residence followed by rapid exit, but they differ in total duration, total clastic thickness, and the balance between iron-rich chemical deposition and carbonate accumulation. The pacing thus arises from the interaction of slow tectonic and carbon cycle controls with faster feedbacks in ice, ocean and atmosphere, all recorded in sequences that integrate timing across continents now far apart. Life persists through cold by occupying places where liquid water energy and nutrients continue to meet, and during cryogenian glaciation, those places exist in thin but durable forms that match the physics and chemistry of an icy planet. The sea ice itself hosts a layered habitat assembled from crystals, brine, and light. As fossil consolidates into congelation, ice pockets of concentrated brine connect into channels that drain and refreeze with the seasons, and inside those channels, microbes grow within films of exopolymer that hold water and solutes against freezing. Photosynthetic bacteria and algae survive where snow is thin, where scattering admits a low blue glow, and where leads and pollineas widen long enough in spring and late summer to allow a brief pulse of higher irradiance. Beneath the ice, a narrow under-ice boundary layer supports cells adapted to low temperature and low light, and nourished by nutrients mixed upward when brine rejection and wind stress overturn the surface. The ice margin is an engine for such mixing because thin covers form and fracture repeatedly, and each event vents gases, cools the surface and draws nutrient-rich subsurface waters toward the light. Farther from margins, refrozen leads and pressure-ridged bands act as recurring skylights that focus the same exchanges in strips. Where tides stir straits and shoals, the cover thins and recurring openings admit more light and allow short pulses of primary production that move carbon into a microbial loop of grazers and decomposers specialized for cold. In places where the cover remains thick and snow-heavy, phototrophy dwindles and cells persist in low-maintenance states, repairing macromolecules, slowly recycling limited resources and relying on dissolved organic carbon that leaks from dying or damaged cells and from microfilms inside the ice. On land and at marine margins, subglacial systems create another set of refugia. Pressure and geothermal heat melt thin water films at the icebed, and friction along fast-flowing corridors maintains basal meltwater that collects in channels and pockets. Their chemolithotrophic microbes harvest energy from reactions between reduced minerals and oxidants, delivered through thin air ice-water pathways, including oxygen that enters at the icefront nitrate and sulfate flushed from weathered belts, and ferric iron produced in micro-oxygenated niches. These assemblages exploit gradients set by water flow rock type and small inputs of oxidants, and persist where hydraulic connections to the margin recur seasonally. Subglacial lakes beneath thick ice on low-relief terrains add longer-lived oases of liquid, insulated by ice and sustained by basal heat and pressure. In their water columns and sediments, microbial metabolism can proceed slowly on redox couples, drawn from rock-water interaction with turnover times measured in years to centuries. At the seafloor, hydrothermal vents and warm springs supply a more robust and continuous chemical power source by delivering reduced gases such as hydrogen and hydrogen sulfide, along with metals and heat. The mixing of vent fluids with cold seawater creates steep gradients that chemolithoautotrophs use to fix carbon without sunlight, and the stable presence of these gradients supports layered communities from vent precipitates to surrounding sediments. Serpentinization of ultramafic rocks within the oceanic crust also generates hydrogen and methane. And where fluids rise into the seafloor, these compounds sustain additional chemosynthetic ecosystems in the absence of light. At shelf edges that remain seasonally open, traditional phototrophic pathways recover for brief intervals and tie to bacterial remineralization that continues in darkness through the winter. In shallow marine belts at low latitude, cryoconite-like aggregates and microbial mats find footholds on sediment surfaces beneath thin seasonal ice-binding grains, with polymers capturing silt that blows or settles through openings and using short windows of light for growth before entering dormant or slow phases. Evidence for these modes lies in textures and microfossils preserved in intervening warm intervals, and in sediments that accumulate within the glacial packages. Organic walled microfossils called acritarchs, which represent a range of eukaryotic plankton, occur before, between and after glacial units, though assemblages thin and diversify unevenly across basins. Filamentous and coccoid forms consistent with cyanobacteria and other bacteria occur in stromatolitic and mat-bearing carbonates that bracket cold intervals indicating continuity of mat-building lineages where chemistry and light allowed. Biomarker molecules diagnostic of eukaryotic membranes appear in some cryogenian successions and point to the persistence of algae in marine settings. Interpretations of specific sterins as evidence for particular animal groups remain debated, so the safe reading is that eukaryotes including algae persist and at times expand in surface waters where refugia enable phototrophy. The ecology of these refugia is shaped by low-temperature kinetics. Enzymes adapted for cold retain flexibility at low thermal energy. Cell membranes remain fluid by adjusting lipid saturation and antifreeze proteins, and compatible solutes lower the freezing point in local microenvironments. Exopolymeric substances in brine channels and at ice-water interfaces trap water and create gels that resist salt spikes during freezing and freshening during melt. Dormancy strategies including cyst formation in algae and resting stages in protozoans bridge dark seasons and multi-year cold spells, and when light and nutrients return briefly, these forms germinate and rebuild thin phototrophic layers. In the ocean interior beneath persistent lids, low oxygen and low temperatures slow respiration and preserve sinking organic matter, longer supporting deep microbial populations that operate on long chemical gradients and that respond to episodic ventilation when mixing reaches them. Nitrogen cycling adjusts to these conditions as denitrification, and anamocs proceed in oxygen-poor layers, closing nitrogen budgets at low productivity. Near polynias and belts of thin ice, nitrogen fixation by specialized bacteria can supplement combined nitrogen when river supply and upwelling are weak, and the availability of iron from glacially ground dust and shelf abrasion can relax micronutrient limits at those same sites. The result is a patchwork of very low productivity across most of the ocean, balanced by narrow corridors of seasonal higher productivity where light iron and macronutrients coincide. On continents, newly cold periglacial belts offer microhabitats in liquid water films around mineral grains during summer thaws, in thin melt lenses in porous sediments, and in sheltered caves where dripping water persists. Endolithic microbes penetrate translucent minerals near the surface using light that filters through quartz or carbonate grains, and exploiting gradients in moisture and temperature at millimeter scales. Where geothermal springs rise through permafrost and along faulted terrain, warm outflows build sinter and travertine that entomb microbial textures and sustain small, persistent phototrophic and chemotrophic communities. In shallow coastal seas that switch between thin ice and open water, benthic mats stabilize during summer and trap silt-building laminae that later cement when cap carbonate conditions arrive, leaving microbial textures at the base of the chemical cap. Food webs assembled on this base are shorter and more microbial than warm ocean webs. Bacteria and archaea conduct most carbon processing. Grazers are predominantly protists and small metazoans where conditions allow, and viruses regulate turnover by lysing cells and freeing dissolved organic matter into the microbial loop. Eukaryotic algae and protists persist in refugia and likely expand during interludes of open water, as suggested by the return and diversification of forms after the cold intervals in several basins. The continuity of lineages across tens of millions of years implies that survivorship strategies suffice in aggregate distributed habitats, separated by ice but linked by currents, and by rare long-distance rafting events. Broad metabolic flexibility in microbe-dominated communities, and the ability to endure long spans of low-energy input through dormancy and slow maintenance. Oxygen availability is patchy through these habitats. Near leads and polynias, photosynthesis and air-sea gas exchange maintain oxygenated surface waters, creating oases that support aerobic metabolisms and downwelling of oxygen into thin upper layers. Farther from openings, waters remain oxygen-poor and anaerobic metabolisms dominate with sulfate reduction, methanogenesis and iron reduction, balancing the limited organic inputs. The coexistence of oxygenated and anoxic zones over short distances creates sharp biogeochemical fronts that microbes exploit, and minerals precipitated at those fronts become part of the geochemical signal that appears in the rocks. In some survivorship during cryogenian cold emerges from a climate that still offers thin but reliable intersections of light liquid water and chemical energy in sea ice, brines, under-ice boundary layers, recurring polynyas, subglacial channels and lakes, hydrothermal and serpentinization systems at the seafloor, periglacial soils and springs on land, and endolithic niches in translucent rocks. Through these settings, carbon fixation continues at low rates, biogeochemical cycles turn on modified paths, and microbial and eukaryotic lineages persist in forms consistent with the physical limits imposed by ice. Field sections on several continents provide concrete windows into how cryogenian ice reaches coasts, how seas breathe through openings, and how the aftermath lays chemical caps. On the island arcs and shelves around what is now Scotland, the Port Ascaig Formation exposes a thick stack of diamictites, sandstones and siltstones that repeats through many cycles. At the base of several packages, scoured surfaces cut into older beds, and bare striations are lined across wide outcrops, and above these pavements sit matrix-supported diamictites with faceted clasts, loanstones within finer laminae, and thin sorted layers that pinch and swell. This vertical pattern reads as grounded ice, advancing over soft sediment, then meltwater sorting at or near the grounding line, and finally quiet marine deposition punctuated by rafting. Interbeds with current ripples and wave-formed structures appear within the muds, showing that storms at times touch the seabed, while ice-still-supplied dropstones a direct sign of nearby open water. The succession continues upward into carbonates that locally display smooth lamination. Ripple cross lamination, early cementation textures and crystal fan relics replaced by dolomite, a set consistent with a cap laid down rapidly in shallow water, fed by high alkalinity after a sharp warming. Across the equatorward cratonic margins of what is now northwestern Canada, the Rapitan group preserves iron-rich chemical sediments interleaved with glaciogenic units. Laminated iron formations alternate with cherty layers and sit with glacial diamictites and muds that bear loanstones and soft sediment deformation. The return of banded iron layers within these stacks implies a deep ocean that becomes oxygen-poor under a lid and then receives pulses of oxidation when mixing or seasonal openings reach depth, while the adjacent clastic beds record the repeated delivery of debris from sea ice and tide-stirred grounding lines. Paleomagnetic work on associated volcanic units constrains inclination values that are low-pointing to deposition at low paleolatitudes during glaciation, and placing cold oceans in the tropics. In Namibia, the Otavi and overlying Nama groups carry classic Marinoan successions. Thick diamictites rest on truncated older platforms, pass upward into finely laminated siltstones with loanstones and occasional wave structures, and are in turn overlain by a uniform thin to modestly thick cap carbonate that stretches laterally for long distances. Within the cap, smooth lamination teepee like buckling tube and sheet voids from early cement degassing, and fans of former aragonite now replaced by dolomite, all point to fast chemical precipitation on a shallow shelf immediately after deglaciation. Carbon isotope values begin very negative at the base, and trend upward, matching a water column that mixes light carbon from isolated deep stores into the surface during the first stages of ventilation, and then drifts back toward values common in open warm seas as weathering and burial proceed. Across Australia, the Elatina Formation in South Australia provides a well-dated glacial unit associated with low latitude indicators. Tidal rhythmites with dropstones record strong tides working in shallow water, while sea ice still supplies loanstones, and the stack includes direct evidence of tidal modulation in lamina thickness, tying sedimentation to astronomical pacing under icy conditions. Above a cap, carbonate appears with the same hallmarks of rapid early cement ripple marks and even laminites draped across paleoslope. In the western United States, the Kingston Peak Formation presents thick glacial packages with striated clasts, deformed diamictites, and interbeds of turbidite sand that suggest repeated grounding line advances and retreats on a tectonically active margin. The cap carbonate that follows shows crystal fan molds and sheet cements, again pointing to rapid precipitation under high alkalinity after warming. In eastern Asia, the Nantuo Formation in China offers Marinoan glacial diamictites, overlain by the Dushantuo cap carbonate, a unit famed for smooth, even lamination, and for a basal negative carbon isotope excursion that diminishes upward. Within the cap, fabrics record early cementation and void formation, consistent with gas escape and crystal growth near the sediment-water interface, and the lateral persistence of these textures across many tens of kilometers fits a chemically driven event in shallow seas rather than a purely local phenomenon. In Oman, stacks of glacial diamictites and interbedded sandstones preserve traction structures and mass flow beds beneath a thin cap that contains roll-up structures, crystal relics, and continuous lamination. The succession records grounded ice marine influence and fast chemical deposition after deglaciation along a passive margin near the tropics. Farther north, the Smalfjord Formation in Norway comprises Tills loanstone bearing muds and rhythmites that pass upward into a cap with sheet cements and negative to neutral carbon isotope values at the base, then gradually more positive values higher up. These paired signals, mechanical below and chemical above, mirror the larger narrative of prolonged cold and rapid warming. Each of these case studies also preserves signs of spatial variability within the cold state. In Scotland and Canada, wave-generated structures occur within glacier marine muds that also carry dropstones, showing that storms acted on shallow beds while sea ice still circulated. In Australia, tidal bundles with loanstones demonstrate strong local hydrodynamics beneath an ice-bearing sky. In Namibia and China, the lateral continuity of cap laminae and the distribution of crystal fan relics argue for wide, shallow seas operating under a shared chemistry rather than a patchwork of isolated basins. Together, the sections show repeated vertical motifs that encode grounded ice flotation and rafting and quiet water settling, followed closely by thin to modest caps, whose textures demand rapid carbonate precipitation in the immediate aftermath. They also show the reappearance of iron formations within the older glacial stacks of some regions, a marker of an oxygen-poor deep ocean during extended isolation. Age control from datable ash and igneous units ties these successions to the Sturtian and the Marinoan. The Sturtian stacks are commonly thicker, include iron-rich layers in several basins, and suggest very long residence times in cold conditions, whereas the Marinoan packages, though still extensive, are often thinner and capped by characteristic carbonates that record a sharp switch to warm alkaline seas. Across the set, low paleomagnetic inclinations captured in interbedded units support low-latitude deposition of both glacial and cap sequences. The case studies thus supply ground truth for the physical and chemical picture. Ice reaches far from poles and works the bed to leave tills and striated stones. Sea ice raft debris into quiet water and drops loanstones that deform soft laminae. Storms and tides at times touch the seabed even within glacial packages, implying openings or thin covers. Banded iron layers return where deep oceans are isolated, and thin, laterally continuous, rapidly cemented carbonates sit directly on glacial beds and carry isotope signals of mixing and recovery as weathering and burial resume under a strong greenhouse aftermath. Uncertainties remain at several linked steps from ice extent to recovery, and these gaps define measurements that can sort among competing pictures of cryogeny and climate. A first open question concerns the global reach and thickness of sea ice. Hard snowball end members envision a near-continuous many meters thick cover across ocean basins with only small skylights, while slushier states allow seasonally recurrent belts of open water at low latitudes and persistent polynyas in corridors set by winds and tides. The rock record permits both in different degrees because wave-worked beds inside glacier marine packages indicate local fetch, while lonestones and finely laminated muds point to long, calm spells beneath ice. Testable predictions follow if low-latitude belts were common. More successions at paleo-equatorial inclinations should contain interbeds with storm ripples and tidal bundles within otherwise glacial stacks, and shelf successions should preserve repeated vertical switches between grounded ice flotation and open water indicators over small thickness ranges. A second uncertainty involves greenhouse strength at the peak of the cold intervals and during the aftermath. Estimates of atmospheric carbon dioxide assemble from proxies that translate mineral chemistry into seawater pH and alkalinity, yet each proxy carries assumptions about temperature, ionic composition and diagenesis. Boron isotopes in well-preserved shallow marine carbonates formed immediately after deglaciation paired with clumped isotope temperatures, and with calcium and magnesium isotope budgets that constrain alkalinity, can yield tighter ranges for carbon dioxide when combined with models that include the geometry of bright surfaces and realistic sea ice optics. A third unresolved issue is the timing and relative weight of triggers. Mafic provinces in the humid tropics uplift of fresh silicates, orbital alignments with weak high-latitude summers, reorganized gateways that change poleward heat, transport dust, cloud radiative effects and methane lifetime changes, all have physical bases, yet the order and dominance likely vary from basin to basin and between the Sturtian and the Marinoan. Denser networks of high-precision ages on ash beds within glacial stacks, coupled with ages on mafic sills and lavas that bracket weathering pulses, can reveal whether silicate weathering sinks lead or lag cooling in specific regions. If basalt weathering in the tropics led the Sturtian onset, one prediction is an early fall in strontium isotopes toward mantle-like values before widespread diamictites, while a supply-side drop in degassing would express as osmium isotope signals that trend toward continental values without accompanying weathering textures in the critical intervals. The internal state of the ocean adds further uncertainty. The return of banded iron formations implies oxygen, poor deep waters during parts of the cold spans, but the vertical and lateral redox pattern remains unclear. Were interiors broadly anoxic with thin oxygenated skins near recurring openings, or were there layered mosaics with oxic corridors that reached depth along tidal chimneys and sills? Iron speciation and rare earth element patterns in iron-rich laminae together with triple oxygen isotopes in sulfate. Within the same basins can separate slow interior accumulation from frequent shallow oxidant inputs. If oxic corridors penetrated to depth near gateways, a prediction is systematic along strike changes in iron minerals and in cerium anomalies that track tidal energy and sill depth, rather than only distance from shore. The structure and thickness of sea ice itself can be tested indirectly. Wave fields attenuate within short distances beneath multi-year covers, so the presence of hummocky cross-stratification and combined flow ripples in multiple low-latitude basins implies seasonal fetch of specific lengths. Metrics that link bedform scale to wave period and water depth can yield lower bounds on open water width, and when tied to tidal rhythmites, they can also yield recurrent scales for openings. If many sections converge on similar fetch estimates at comparable paleo-latitudes that would support organized belts rather than isolated skylights. Albedo feedbacks depend on impurities in snow and ice, yet the amount and distribution of dust and volcanic ash during the cold spans are imperfectly known. If dust loads over low-latitude snow were high surface darkening would lower albedo and favour local melting. If dust travelled mainly beneath bright cloud decks and settled into the ocean, planetary reflection could increase instead. Dust provenance traces in fine fractions of glacial and interglacial beds, together with model reconstructions of wind belts for specific paleogeographies, can resolve whether major dust plumes overlapped expected open water corridors. The prediction is a spatial pairing. Dark and snow signals such as melt crusts with mineral inclusions should co-occur downwind of large interior basins, whereas enhanced marine cloud brightening would register as fine dust spikes within pelagic muds away from those plumes. Biological persistence leaves its own uncertainties. Microfossils, biomarkers and matte textures show continuity, but the relative roles of underice phototrophy, subglacial chemolithotrophy, and hydrothermal ecosystems are not yet apportioned. Compound-specific isotope analyses of algal sterols and bacterial hopanes through glacial intervals, paired with microtextural mapping of brine channel faces, and with trace metal proxies for nutrient supply, can test whether phototrophy spikes coincide with sedimentary signs of thin ice and leads. If under-ice-light regimes dominated low-latitude shelves, a prediction is synchronous enrichments in photosynthetic biomarkers beneath horizons with wave work, while subglacial dominance would pair chemolithotrophic lipid signatures with tills that carry pressurized meltwater features. Dating and correlation present further uncertainty. Some successions carry few ash beds, and metamorphism erases primary signals in others, so durations of residence and synchronicity of deglaciation across continents are imperfectly defined. Wider application of uranium-lead dating on zircon in ash layers combined with rhenium-osmium dating of organic-rich units and with high-resolution magnetostratigraphy can tighten correlations. If the base of cap carbonates on several continents proves synchronous within narrow bounds that would support a rapid globally coordinated deglaciation, if instead ages scatter by several million years in a pattern tied to paleogeography that would support staggered retreats controlled by regional albedo and gateways. Cloud feedbacks under unusual aerosol and dust fields are also weakly constrained. The balance between cloud brightening by sea salt dust and sulfate in cold states, and cloud reduction over warm open water during the aftermath, affects both entry and exit. Ancient cloud condensation nuclei leave no direct rock record, but sulfur, multiple isotopes in sulfates, can reflect oxidation pathways and ultraviolet exposure, while salt assemblages in fluid inclusions can track marine aerosol composition. A prediction is that basins downwind of strong polynyas will preserve sulfates with signatures of low-altitude oxidation and higher halite inclusions, whereas interiors will preserve signals of stratospheric processes associated with volcanic injections. Paleogeography is reconstructed with error. True polar wander rotation paths and sparse paleomagnetic poles allow multiple fits of continents, and small gateway width changes matter for heat transport. Better constraints on apparent polar wander paths through new poles from well-dated volcanics coupled with fits that honour margin geology and sediment routing can narrow the maps. If equatorial shelves were as extensive as some fits, propose more low-latitude tide-dominated faces with dropstones should emerge in cores from predicted corridors. If not, their scarcity would argue for alternative fits with broader equatorial seaways. Deep carbon sources and seafloor sinks carry additional uncertainty. If ridge production slowed, or arc metamorphism waned during parts of the cryogenian carbon dioxide supply would have dropped. If hydrothermal circulation intensified or waned, seafloor weathering sinks would have changed. Osmium and strontium isotope curves tied to dated mafic rock volumes can bracket these terms. A prediction is that intervals with low mantle osmium input and high continental strontium coincide with onsets if supply-side reductions helped cooling, whereas the opposite pairing would implicate enhanced weathering sinks. Finally, the mechanics of cap carbonate formation invite tests of kinetics and water column structure. Early cements, crystal fan relics, sheet cracks and basal, negative carbon isotope excursions point to rapid precipitation from supersaturated waters mixed with light carbon from depth. Yet the balance between seawater precipitation and pore water cementation varies by basin. Microfabric mapping at micrometer scales paired with clumped isotope temperatures, calcium and magnesium isotopes and pore fluid diffusion models can distinguish water column precipitation from early diagenetic cementation. If water column precipitation dominated fans and laminae should align with wave and current indicators and show uniform temperatures across facies belts. If pore waters dominated temperatures and fabrics should vary over short distances tied to permeability and early cement pathways. Across these themes, each uncertainty corresponds to concrete observations that can be sharpened tighter, ages, broader facies maps at low-latitude paired isotope systems that track redox and carbon pools, biomarker suites tied to habitat and physics-based reconstructions of ice thickness, tide fields, and wave fetch. The questions are specific and the predictions comparative. They ask whether low-latitude belts repeat across basins, whether proxy-derived greenhouse thresholds match model energy budgets, whether iron and sulfur cycles align with predicted ventilation corridors, whether biomarker pulses track openings in the cover, and whether cap fabrics record water column or pore scale precipitation under a super greenhouse aftermath.